Okay, so here's the last video for the course. I'm going to be talking about waves that are supported in a magnetized plasma. So if you remember in the previous video, we did waves in an isotropic plasma. And by isotropic, I meant there's no preferred direction. So the moment you have an external magnetic field, because the Lorentz force has a magnetic term now, which is important, suddenly the plasma is not isotropic anymore. Now it really depends how your waves are oriented with respect to the magnetic field. So it becomes an anisotropic plasma. And we're going to talk about, in some simple cases, what kind of waves this plasma can support. So before going into that, I just have one clarifying comment to make about isotropic plasmas, which we did in the previous lecture. So if you remember, even in the cold plasma case where we had no pressure term in the momentum equation, I refer to the solutions as longitudinal waves. I mean, to be sure, you need a spatial dispersion for a wave to propagate. So if your dispersion relationship is just omega equal to omega p, where omega p is the plasma frequency, there's no k in that term, there's no wave vector, so that you don't really have a real wave which is propagating. Okay, so the intuition you should have for that is, if you create a displacement in the plasma, it just oscillates in place where you created the displacement. It's not propagating as a wave. You really need that restoring force from the pressure of the plasma uh, for you to get a dispersion relationship of a wave which has the wave vector k in it, right? So I've called everything longitudinal waves, but just be aware that only in the second case, where we actually took into account the pressure of the plasma, did we actually get waves in the traditional sense of something that propagates and carries energy. Okay, so let's come to cold magnetized plasma. So the only difference here, again, we're going to follow the same framework, but the only difference in the momentum equation or the Lorentz force equation is that we have some external magnetic field B naught. Okay. Again, E is the self-consistent electric field in the plasma. So it's the electric field carried by the waves, which we are going to solve for. The waves also have a magnetic field B, but because B and E have the same magnitude, and we are assuming that V is far, far less than C, again, we're going to neglect, as we have done in most of the course, we're going to just neglect that term. But the external field B naught, which is a uniform field, it's not a wave. I'm just assuming that it's a static uniform field. This can be much larger than the electromagnetic field of the wave itself. So even though V is far, far less than C, B naught can be far, far greater than B or E, right? And so we can't just neglect this term. So we're going to keep this term. Just like we did when we solved for the dynamics of a charge in an external magnetic field. You saw that the charge goes in circles, right? So a lot of the algebra will proceed similar to that. Now again, we go to the Fourier domain. Um, we are assuming that all quantities vary harmonically. I mean, we can do that because these are just linear differential equations. So you can always solve them by going in the Fourier domain. And again, we have the equation for the current. The current density is just elementary charge times the charge density times the velocity. So we can get rid of the velocity in this equation and just retain and write this equation just in terms of J, the current density. So I've done that here. Again, you can always pause and then check the algebra yourself. Just to make the notation simple, and because we have some forethought now, that we're going to end up with a dispersion relationship which will depend on the fundamental frequencies of the plasma itself. So one of them is the frequency of plasma oscillations, which we spoke about last lecture. Now we're going to have a new frequency term because we now have an external magnetic field. So I'm going to call omega the cyclotron frequency, so QB naught by MC. And I'm just going to write all of this equation in terms of the frequencies. Instead of the charges, densities, masses of the electron, and just to have a algebraic shorthand, and also it gives you better intuition. Okay, so again, you can pause and check the video here, but I've just written the same equation now in terms of the frequencies. So you get a vector equation relating J and E. So this is your Ohm's law basically, which is J equal to sigma times E, where sigma is the conductivity, right? So we have something, we basically have Ohm's law here, but it's just more complicated because of this cross product here. So we can just write them out as the X component, the Y component, and the Z component of these equations. So we have get three equations, three scalar equations, which are just decompositions of this vector equation. along the three axes. And then you'll see that Jx is related to Jy, Jy related to Jx. Again, this is very similar to what you did with cyclotron motion, where you had that coupling between the components X and Y, and the magnetic field was in the Z direction. So we have exactly the same setup here. So we'll use the same tricks. We know that in the end, you're going to get some kind of a circular motion. So you need to change the basis vectors. The Z vector can remain the same, but the X and the Y can be changed to left and right hand rotations of the vector. So left and right hand polarization. So I'm going to call that plus and minus here. So I'm going to change the basis vectors to J plus is Jx plus Ijy, J minus is Jx minus Ijy, where I is the square root of minus 1. Okay. So in the same way, I'm going to have the electric field also decomposed into its plus and minus components. So they'll turn out to be the components will turn out to be left and right hand circularly polarized components. So instead of Cartesian basis, you're choosing basis which are plus and minus here. That's all. I mean, nothing else changes. It just decouples the equations. That's all it does. Okay, so you write all of that out, and you get the first equation, which is J plus is now related to E plus with a simple scalar factor in front of it. So we've decoupled the coupling between Jx and Jy, and now we have a simpler equation because J plus only depends on E plus. There's no Jy here, or let's say J minus, other components of J. So you do the same for J minus, you get something like this. The only difference is now the sign has changed. So instead of omega, the small omega plus capital omega, where this is the cyclotron frequency, you just have minus of the cyclotron frequency. Okay, so you can write Ohm's law now as a matrix equation, right? So before we always had a scalar equation because the vector J was always parallel to the vector E, but now it turns out that the vector J is not always parallel to the vector E. So instead of having a simple scalar conductivity here, we now have a matrix. But of course, because we have gone through the trouble of decoupling the equations, the matrix is diagonal, right? So in this basis, again, it'll turn out that Jx scales only with this has to be J plus J minus and Jz. So I made a mistake here. This is plus and minus. So it'll turn out that J plus is always parallel to E plus, J plus, always scales with E plus, Jy scales with Ey. But of course, the scaling is different, right? So there's a sign difference here. So you get some kind of a tensor equation, which is just matrix multiplication, and the sigma, the conductivity, instead of being a scalar, it becomes a tensor in this case. Okay. So we can, again, once you have Ohm's law, you know what to do, right? You go back to Ampere's law and Faraday's law, the Maxwell's equations. You take curl of one in the Fourier domain. You take k cross of one, and then you substitute the other. You'll be left with J, and then you use this equation to get rid of J in Ampere's law. And now you have an equation purely in terms of the electric field. So you get a differential equation, second order differential equation, which only has the electric field. So I'll skip the algebra because you already have the intuition of how to do this, how to go about getting the wave solution from Maxwell's equation. So there's no point just repeating the algebra. So I'm going to skip it, and I'm going to write the final equation which you get. It'll turn out that the final equation is actually really becomes algebraically very complicated. So it's you just get a very difficult term to deal with, difficult amount of algebra to deal with. It's likely even going to be hard to write it on a sheet of paper. But we'll just take a simple case so we get some intuition for what's happening. So I'm going to take a simple case where the wave is propagating along the z-axis. Okay, so this is not a general case anymore. It is a particular case because I have made the magnetic field, the external magnetic field B naught, and the wave vector parallel. I've put both of them along the z-axis. Okay, so this is a very particular case. Now, in that case, the wave equations become very simple. So this would be the equation for the electric field, and I've just decomposed them in the vector equation into the three scalar components. So Z, E plus, and E minus. You'll immediately notice that the equation is very similar to what we had before if I put this capital omega equal to 0. right? Which makes sense because if I just put the magnetic field equal to 0, then the plasma again becomes isotropic. You'll get back the dispersion relationships you had. But now let's actually look at the solution. So the first solution, of course, well, non-trivial solutions where not all three components of the electric field are 0. So the first solution, of course, is to have E plus and E minus equal to 0. So remember, E plus and E minus are in the transverse plane to the direction of propagation, right? E plus and E minus are in the XY plane. The direction of propagation is along the Z plane. So you get a longitudinal solution. So you only have EZ, which is a longitudinal component. And you get back the same relationship. You get omega equal to omega p. And that makes intuitive sense because as long as you displace the plasma along the magnetic field, there is no Lorentz force, right? The Lorentz force is V cross B, and if V and B are parallel, then there's no Lorentz force. And so you get back the old solution you had, omega equal to omega p for plasma oscillations, right? Again, these are plasma oscillations. If you put in a pressure term, then you actually get a real wave which will propagate, where the dispersion relationship will have a k in it, a wave vector in it. But these are the plasma oscillations which we already studied in the isotropic case. Now the second case here is going to be, oh, let's say EZ and E minus are 0, right? So EZ and E minus are 0, which means this term has to go to 0, and that's the dispersion relationship, and then you can have any E plus you want, right? So that dispersion relationship is written here. Now notice again that if I set this capital omega to 0, I get back my transverse electromagnetic wave from the previous video, right? Now, the new thing with the magnetic field is now I have a third solution, which is not degenerate, where I set E plus and EZ equal to 0, and I can have any E minus I want as long as this factor is 0, right? And that factor again gives you a third solution. So in the isotropic case, you only had 2 unique solutions, right? But in this case, you have 3 unique solutions. And the reason for that is solution 2 and solution 3 were degenerate in the isotropic case. And you can see that they're degenerate if I remove this term here, right? You get back the same dispersion relationship. So they're the same waves. So what the magnetic field has done is it has created 3 possible solutions, 3 possible types of waves. So one of them is the longitudinal oscillations. The other 2 are transfers, but they have different dispersion relationships. So solution 2 is one hand of polarization. So let's say the electric field rotating clockwise, and solution 3 would be the electric field rotating anti-clockwise as the wave propagates, right? So these are the left and the right hand circularly polarized radiations. Again, what is defined as left and right is a matter of convention. We're not going to go into that, but just know that the two-handedness, that left and right circularly polarized waves have different dispersion relationships. And the reason for that is that the electrons have a sense of rotation when they perform cyclotron motion. So if you have a magnetic field directed along the z-axis, and when the electrons perform cyclotron motion, they go in a certain sense, right? Protons go in the opposite sense. Now, if you have the electric field also rotate in the same sense, it'll have a different effect. The electrons will have a different effect on that electric field than if the electric field is rotating in the opposite sense to the electrons. They're going to have a different effect on it. And that's the reason why you get 2 different dispersion relationships for the waves. Now, in class, we'll do a problem where we'll show that this actually leads to, this actually is what is canonically called the Faraday effect, where if you take a linearly polarized wave, then its plane of polarization rotates as it propagates through a medium, which is magnetized. And so we call that the medium is birefringent, and the effect is called Faraday effect or Faraday rotation. So it turns out that if you have left and right circularly polarized waves, which are traveling with different phase velocities, now you'll show in class that the net effect of that is to rotate the plane of linear polarization. So we'll do a problem in class which will make it obvious. But just know that this is what is called birefringence or Faraday rotation. Now, if you notice, we took a particular case here where we said that to simplify the algebra, we said that the wave vector propagates along the z-axis. Now, that need not be the case. The wave vector can go in any angle with the with the magnetic field. And so you again get these kind of wave dispersion relationships. You get three different solutions, but the algebra is much more complicated in the general case. There's also, we can also take another particular case where K is perpendicular to B, and then you recover some, that's called transverse propagation, and you recover something called the Cotton-Newton effect. And again, we won't have time to really delve into the details of these effects, but because the Faraday effect is so commonly observed, I thought it was worth you knowing about it and what the background of the Faraday effect is, where for longitudinal propagation, where K and B naught are parallel to one another. So we'll do some problems in class which will give you a little more intuition for what is the consequence of having these two branches, these two dispersion relationships possible for transverse electromagnetic waves. So now you really have, you can think of it as two different eigen solutions. You have two different types of waves which can travel, and they're both transverse electromagnetic waves.